Space log day 474th and a half. I've been lost in space for however many days I just said. And you know what we haven't done yet? We haven't done tangents. So let's do some tangents. So last section we talked about the graphs of sine and cosine and stuff like that. So we haven't really talked about tangent yet, right? So here's our example, or I guess spark your learning. You can use a sundial to tell time by observing the shadow. And let's see, the top of the planet cast shadow is 2 feet above the ground. The angle of the sun changes over time, which affects the length of the shadow as well as its position. What mathematical questions? What are they going to tell us? I'm curious. So along the equator, when the sun is directly overhead at solar noon, the shadow has length of 0 feet. For each hour after the solar noon until sunset 6 hours later, the angle between the pointer and the shadow it casts increases by 15 degrees per hour. I guess that uses tangent, does it? I don't know. Either way, let's go use tangent. Sine over cosine, but we're going to find something kind of interesting. So it says graph the basic tangent function, and remember that the tangent we can define as sine over cosine. And so we can think about sine over cosine at like angle equals 0. So like that's going to be 0. But something weird happens as we go around the circle. So like when we start to get here, what happens when we get here? So in that situation, we have so again, it's sine over cosine. So our sine is going to equal 1. And then our cosine at that point is going to equal 0. That seems bad. So you obviously can't have a 0 underneath a fraction. So what's going on here? So it's undefined. So here's our table that we were kind of talking about. And so we notice that 0, 0 goes to the origin. As we go from 0 off to the negative side, we're going to hit -1. And then it's going to go undefined. So that's bizarre. So it says, using the unit circle and values in the table, what do you observe about the range of the tangent function? So remember, the range is our y values, or the horizontal line test. From the values in the table, the range of the tangent function appears to be -1 to 1. I mean, from the table, maybe. I know it's not true, but from the values in the table, the range of the tangent function appears to be multiples of... No, I don't agree with that. From the unit circle, there are values of theta for which the ratio y over x becomes very large or very small, which suggests the range is likely all real numbers. I like those two. Or not. Did I not read this one? From the unit circle, the range is likely all real numbers except 0. Okay, that one's not right because there's a bunch of the other ones. Let's try that original one. Cool. So again, from the values in the table, the range looks like -1 to 1. It's not that. It's more of something like this statement. But let's continue on. What appears to be the domain of the tangent function? So here is where we have some theta values or our x values where we do not have a y value. So the domain is not going to be all real numbers. So we could say it's all real numbers except for positive and negative odd multiples of, is that odd multiples? So like 1 and then times 2, 3, I wouldn't say odd multiples, but we'll come back to that one. The domain appears to be all real numbers except for negative odd multiple. No. The domain appears to be all real numbers including negative. Nope. The domain appears to be whole numbers, but not all. We'll stick with that. So it's a weird way of saying it, but they're talking about this guy and this guy. And there's a pattern there. Some values of the tangent function are undefined. What do you think the graph's going to look like? Whatever. So here is our graph of tangent. Look at that. That's crazy. So remember, our dotted lines are asymptotes. So we can again rethink about our domain and range. Now we have a graph in front of us. I guess I can't use red. So if we do our horizontal test, we can put a horizontal anywhere we want, and we're going to cross one of the lines, right? So our range is all real numbers. However, if we do the vertical line test, we're going to hit, whenever we hit these dotted lines, tangent is undefined there. So our domain is all real numbers except multiples, or I guess wherever they said odd multiples. So let's see, pi over 2 times 3, yeah, something like that. So there's going to be some domain issues. So keep that in mind as we move forward. Let's see, identify some major characteristics, domain, range, intercepts, intervals of increasing and decreasing. So where does it cross the x-axis and y-axis? So we've got 0, 0, that's probably going to be something we use. And it crosses at pi, 2 pi, negative 2 pi. And like side to side, that's 1, right? So it's like pi over 2, pi over 2. So these are all good things to kind of know. And it is increasing or decreasing, positive or negative. So is it increasing or decreasing? It is always increasing. Look at it. As you move left to right, it's always going up. It's always going up. I mean, obviously there's an asymptote, but it's always going up. So it's never decreasing, and it's negative and positive. So we're the location of 2 vertical asymptotes. Okay, we talked about that. Is the tangent function odd, even, or neither? I don't know. I don't remember the definition of odd or even. Clearly, I don't remember because I messed it up so far every single time. I'm going to say it's odd. I think it's odd because the function is symmetric around the origin. Ha ha! Ha ha! Ha ha! Ha! I mean, I knew that. You might imagine this tangent thing is going to get a little goofy. So recall that our sine, cosine, we had our A was our amplitude and 1 over B. I'm not going to forget it. I'm not going to forget it. I'm not going to forget it. Our 1 over B was our period. So again, with sine and cosine, our amplitude stretched it vertically. So the A stretched it vertically, and the B, 1 over B, stretched it horizontally. I think that's going to be the same with tangent. However, it's going to get a little interesting. So, and because or what's going to get interesting is as you stretch it, you're going to have to use reference points. And so that's why I mentioned that. So vertical asymptotes and reference points are the big things that we're going to be working with. So again, our generic function is a tangent of 1 over b times x. The vertical asymptotes closest to the y-axis are x equals negative b pi over 2 and positive b pi over 2. So sine cosine, it was like b times 2 pi. Tangent, it's b pi over 2. I'm totally going to remember that. I admit it's going to be tough. I'm going to get them confused. But our graphs, we've got on the left, let g of x equals negative 3 tangent of 2x. And on the right, we have h of x equals 2/3 tangent x over 3. So let's start over here on the left. So they're throwing a lot of stuff at us all together, all at the same time. Which I guess they have lots of faith and confidence in us. I don't know if I have that much faith in myself. Anyway, moving on. So step 1, our parent function is this blue graph. Okay, so that's what our quote-unquote normal tangent looks like. Our new graph looks like this right here. So notice how there's reference points. So on our parent function, the reference points are at y equals negative 1 and 1. So 1 right here and 1 right there. So we have to work with what we have to figure out where the new reference points are going. So step 1, I am going to do it in yellow, but you'll be okay because it's just a negative sign. So just the negative sign flips it around. Okay, so this does a vertical stretch. Yeah, a vertical stretch. So since it's vertical, it's going to be reflected around the x-axis. So if our green is our initial points, our yellow is our new reference points. Okay? So then let's use black for our 3. So that 3 is a vertical stretch. So remember, our new reference point is at negative a, positive a. Which is the same for sine and cosine, but it's a much easier just because the amplitude changes. But anyway, so the 3 is a vertical stretch. So that means instead of 1, it's going to be all the way up here at 3. And again, we're on the other side of the x-axis because of that negative sign. So last but not least, we've got, I'm out of colors, blue-green again. We've got this thing that we have to deal with. So up above, we saw that all the way up here, for f of x equals a tangent of 1 over b x. So we have our x. So 1 over b x equals 2x. X's cancel out. B goes the other side. So b is actually equal to 1/2, not 2, which is where I get horribly confused. But whatever. So that means that our horizontal, I guess, compression at this point is by 1/2. So you can either remember that, so it started here and then it's going to go halfway in between. Or we do have a formula. The reference points are located at negative b pi over 4. So let's line this up. Close enough. So negative b pi over 4. So negative 1/2 negative b pi over 4 is pi over 8. My handwriting is so good. Which is where we go from the yellow dot into the green dot that is actually on, whoops, there. No? There. The black dot, I tried. It was going to be so clever. The black dot that is now on the green dot that is on the red line. So there's two ways that you can think about this. You can think about it of, same thing with all of our other transformations that we've been dealing with. You can think about it as vertical and horizontal stretches, or you can think about it as, I need to remember this these three equations. This one, which is probably easy to remember, your asymptotes and your reference angles. So whatever works best for you. I don't know. I kind of like the vertical horizontal thing, but we'll see as we go through these problems which one I default to. So that was the left. So the one on the right, again, let's look at it. Let's analyze it. So I'm walking you through this because this is a good learning process. You have an example, so you got to pick out everything in the example. So h of x is 2/3 tangent of x over 3. So if we were to do it analytically, using just the formulas, so I don't even need the graph. We're just going to put it up here. So our A equals 2/3. Our B equals 3, because remember this guy right here. So 1 over B equals 1 over 3, and then however you want to do that algebra to make it make sense in your head. Doesn't matter to me. So then we have our vertical asymptotes at x equals, in this case we can probably just do plus or minus. Plus and minus, I should say. B, 3 pi over 2. And then our reference points are going to be negative 3 pi over 4, negative 2/3. I'm getting that from right there. And then my second reference point, whoops, not that one. My second reference point is right there, is not negative, is 3 pi over 4, 2 over 3. So that's kind of the analytical approach, if you will. Whoops. Eraser, go. So now that I have all that information, I can kind of check my work here on the graph. So we've got our new reference points, negative 3 pi over 4 and negative 2/3. Negative 3 pi over 4, negative 2/3 is equal to that. Yeah, verified. Just checking. Again, it goes through 0, 0, and then our second reference point is right here. And then we have our vertical asymptotes at negative 3 pi over 2 and 3 pi over 2. So either way works. We'll see which one's easier. I don't know the answer to that. Let's answer some questions. How is the transform function g of x different from the parent function f of x? G of x is the one on the left. It looks like they're talking about increasing and decreasing. G of x is always decreasing instead of increasing. Describe how period, domain, range, and location of the vertical asymptote reference points have changed. So we've kind of went over all of that, so I'm not going to worry about typing that in. How is the transformed function h of x different from the parent function tangent of x? So again, we've kind of talked this one through. Well, no, we did it analytically, but if we were to talk it through, again, our blue one is our normal parent function. Our red one is a horizontal stretch because of the 1/3 inside of there, because the b is 3. So it's a 3 times horizontal stretch. And then is a vertical compression because our a is 2/3. So it's less than 1. Which is why our reference points, they start up here at 1 and they actually get closer to the x-axis a little bit because of that 2/3. What are the corresponding values of Okay. Let's see here. On the left, a is equal to -3. B is equal to 1/2. On the right, a is equal to 2/3. B is equal to 3. I was just mad because I had written all those down, and then they finally asked me about it. Oh, I forget which one's which, too. Gosh dang it. G of x, h of x. Stupid scrolling. Whatever. Dummy. So a -3 goes with g of x. A 2/3 goes with f of x, or h of x. I'm going to go down there. See if that works. B 1/2 is for g of x. I wonder, I'm still pretty sure that I'm actually right, but I was just trying to mess with them, so see if that goes there, and that goes there. Yay! Oh, computer programs. Can't live with them. I guess you actually kind of can't. We have for generations, but... let's see. When will the distance between the vertical asymptotes of a transformed tangent function of form g of x be greater than the distance between vertical asymptotes of the parent function? So the asymptotes would be part of a horizontal stretch if they're going to be greater, and the horizontal stretch is the inside. So it is going to be when b is greater than 1. All right, so we are going to attempt to create our f of x from a graph. So we're going to look at a graph. We're going to hopefully try to figure out a function based on that graph. So you can write tangent equation in the form blah, blah, blah. So identify the value of b from the spacing between the asymptotes. The separation between any two consecutive asymptotes is b pi. Once you identify b, determine a by evaluating tangent of x over b at a recognizable point on the graph, and then solving f of x. Oh, good, we get to do a little bit of math. So here we go. So look at the graph of a tangent function and write an equation for the graph in the form f of x equals a tangent of 1 over b. So it told us, so the distance between the asymptotes is b pi. So we can look at these, at the distance here, and that is from -pi to pi. So that would be, what, 2? 1, 2? 1 pi, 2 pi? So is b pi equals 2 pi. So b equals 1. 2. What am I thinking? 2. So now we can do some algebra and figure out the rest. So what we have now is, and hey, I'm going to pick an easy point right there. Why not? Tangent of 0 is 0. You can also use this. This looks like a reference point. You can probably either use either one of them. I doubt that it matters. But we have, actually you probably wouldn't want to use the origin, because that won't give you a. Okay, fine. So we have a function, a tangent of 1/2 x equals, let's see, what point did they use? Did they use the reference point? So there's our b equals 2. So that's what we were doing. So use the point. So it's use the labeled point that's on the graph. Negative pi over 2, 2 on the graph to find a. So that is our x. We're plugging that in, and that's going to equal 2. So we have 2 equals a tangent of 1/2 times a negative pi over 2. And then we want to evaluate tangent, shove it over to the other side, and we're good to go, right? So I'm going to look at my little unit circle. Once I simplify all of this, we're going to have a tangent of negative 1 over 4 pi, or pi over 4. Pi, negative pi over 4. That would be like a 45-degree angle, in case you're wondering. I knew that, totally. And the tangent for that, opposite over adjacent, is going to be 1. And since it's negative, it's going to be negative 1. So now we have 2 equals a negative 1, divide times whatever by negative 1, both sides, you have negative 2 equals a. Oh, look, that's what they got too. I love algebra. That makes me so happy. So then we plug everything in, and here is our equation. So let's hear, could you use any point on a graph? So what would have happened had we used 0, 0? So in that situation, a wouldn't have mattered. A could be a billion in this situation, and it would still be 0, 0. So I would say no, the slope is not constant. No, okay, fine. No, solve A is when you have 2. Really? Okay, now I'm curious. Can I use 0, 0? So we're going to try it real quick. A tangent of 1 over b x equals y, I guess, whatever. So then we have a tangent of x equals 0, so it's going to be 0, equals 0. So then tangent of 0 is opposite over adjacent, which would be 0. So so I don't know, man, I disagree with them. 0, 0 doesn't work. Just saying. Whatever. How can you find the value of tangent of negative pi over 4? Select all that apply. You can use a calculator. You can use the unit circle. I don't know why you would use inverses, I guess, but whatever. So you can always shove it all into your calculator, make sure it works. Plug in some known points. You have at least 2 known points, 0, 0, and the one they give you. So when it says how can you use the values of a and b to check your equation, reference points I think would be a good answer for that. There's a variety of ways. So this little part here, compare tangent functions represented differently. So let's say you did an experiment and you have a table of data and you didn't necessarily know it was a tangent. Maybe how would you figure that out? I guess, I don't know. But for example, asymptotes are easy to identify from graphs, equations, or tables. You can determine the period from the location of 2 consecutive asymptotes. So here we have a table, and you will notice that you have an undefined, and then you have another undefined here. So that gives you your 2 asymptotes, which then gives you a period, which then means you can make as many asymptotes as you want from that. So in this case, the period is 1. No. Yeah, 1. Right? So asymptote. Yeah, it's 1. Starts at negative 5 pi over 8. And then, or I guess it goes, or it moves over 2 times 5 pi over 8, which I guess would not be 1. I don't know what I was thinking. Anyway, but you've got your 2 asymptotes. And then, I mean, from there, if you wanted to make an equation, you have 3 known points. And you're good. You can figure it out from there. So here's a graph of what they were talking about. So how can you identify vertical asymptotes of a tangent function from a table? They are located at the x value where the function is undefined. I don't know what number they want there, but we're just gonna at the points. Okay, yeah, I'll give you that. Where the function is undefined. The important there is where it's undefined. How can you identify vertical asymptotes of a tangent function from a graph? Select all applied. Look for when the denominator is -1, false. They are sometimes indicated by solid lines, false. They are located where there are breaks in the graph, that could be true. They are sometimes indicated by dashed lines, also true. Subtract 2 consecutive asymptotes to find the period of the tangent function. So 5 pi over 8 minus -5 pi over 8 is equal to 10 pi over 8 equals 5 pi over 4. So I was wrong. Problems, right? So create models with tangent functions. So you can use a tangent function to model real-world problems that involve a perpendicular measure expressed as a function of changing angle. So let's say you have a climber, you're climbing, you got a friend here, and that friend can, one, point a little laser or line of sight to figure out the angle, and then that friend might have one of those little range guns that you point at it and tells you how far away it is. Those things exist, I promise. So that person can figure out what this hypotenuse is, and then if you have a function, a tangent function, you'll be able to instantly poop out how high up that climber is. So that maybe you're talking on his earpiece or something, I don't know, like, hey man, you're almost there, you only got like 20 feet left. I don't know. But so, and then this you can just easily measure. From the diagram, you can see that the height h of the climber and the distance 150 feet form two legs of a right triangle. Use this information to write tangent theta as h over 150. So again, tangent is opposite over adjacent. Okay, so we've got that. Why do you use h instead of 500 in this equation? So 500 is the total cliff size. H is how high your climber is up. I mean, he could only be like 1 foot off the ground for you. I don't know. Maybe he's a bad climber. Use h instead of 500 because the cliff may not be perfect. Nope. Use h instead of 500 because the height of the climber changes over time. H is the height of the climber once they reach the top of the cliff, which is true. And there you go. So the tangent function h equals 150. Tangent theta gives the height of the climber as a function of the observer's viewing angle. So this is what we're looking at. They graphed it because, that's what we do. So this is the elevation. This is your elevation angle in degrees, and your height. So you're 60, because they asked about 75. So yes, it may not. I don't think it will eat 75. How can you find the maximum viewing angle? Look at the graph to identify the x value and the y value of 500. That won't work. That won't work. Look at the graph to identify the y value. Yeah, we're going to stick with that one. Appears to be at about 74 degrees. Yeah, totally, because that's exactly what I thought. What calculators are for. In the context of the situation, what does the dashed line at 90 degrees, at theta equals 90 degrees represent? The dashed line at 90 degrees would be like, I don't know. So like if you imagine your theta at 90 degrees, means your friend is looking straight up, and you would have to literally be inside of the cliff to be able to do that, which would be false. So the dashed line represents a hyperbola that meets a curve. No. Dashed line is an asymptote. That means the viewing angle could be more than 90 degrees, but less than 180. Because in theory, if the climber climbed high enough, they could be directly above the observer. No, they could not in this situation. Oh, and what does the point 00 mean? Represents the minimal possible view. No. Represent the point 00. So that I will agree with. The dashed line is an asymptote. Could never be 90 degrees because the climber could never climb high enough to be directly above the observer. The point 00 represents the maximum possible viewing angle. No, 00 would be right there. I guess the minimum possible viewing angle? Oh, yeah, there you go. So there you go. Try some examples out yourself, and wait, hang on, and see how it goes.